Lesson 5, Making Connections, Logarithmic Scales in the Physical Sciences. Logarithmic scales provide a convenient method of comparing values that typically have a very large range. Several phenomena in the physical sciences can be described using logarithmic scales, and these include the pH scale, the Richter scale, and the decibel scale. Okay, so the pH scale looks at the concentration of the hydronium ion for different acidity levels. The Richter scale looks at how intense an earthquake might be, and the decibel scale looks at sound and intensity of noises. Okay, so to compare concentrations on the pH scale, the intensity on the Richter scale, or sound intensities, you will need to determine the quotient between the values that are being compared. And so remember, quotient means that you are looking at division. And so we'll look at some examples of each of these so that you can see how the logarithmic scales actually work. Okay, the first scale we're going to look at is called the pH scale. And the pH scale is defined as pH equal to the negative log of the concentration of the hydronium ion. So H plus is the hydronium ion concentration in a substance. Okay, so you are familiar with the pH scale. A pH of 7 represents a neutral pH. And so something like pure water has a pH of 7. And then the lower the pH, the more acidic it is, and the higher the pH, the more basic it is. So that's something you're familiar with in your general science courses. And so what we're going to look at is when you have something that has a pH of 3, like grapefruit or orange juice, versus something that has a pH of 4, like tomato juice, we're going to see how much more a hydronium ion concentration there might be, even though the pH only has a difference of 1. Okay, so we're going to see how a logarithmic scale is applied here. So for example 1, it says find the pH for tomatoes if the hydronium ion concentration, H+, is 6.3 times 10 to exponent negative 5 moles per liter. So we're going to look at each of the different questions on a separate sheet of paper. So starting with the first question. So what we're told in question number 1 is that we're looking for the pH. And we're told the concentration of the hydronium ion. If you can just correct that on your sheet. I know it says hydrogen. It should have said hydronium. And so what I'm going to do is I'm going to use the formula for pH. And that's pH equals negative log of the concentration of H+. And I'm going to replace the concentration of the hydronium ion, given the information that was in the question. So I have 6.3 times 10 to exponent negative 5. And if I do that on the calculator, I get a pH of about 4.2. Okay, so therefore the pH for tomatoes is about 4.2. You can see that on your scale as well. On the previous slide, the pH, the concentration, the pH for tomatoes is about 4. Okay, tomato juice is about 4, so the pH for just tomatoes might be about 4.2. Okay. Okay, for part B, it says if the pH of seawater is 8.5. Determine the hydronium ion concentration. So this time I'm told the pH, and I'm looking for the hydronium ion concentration. So for that question, so I know the pH is 8.5, and I'm looking for the hydronium ion concentration. So I'm going to start with the formula again. And so what I'll do is I'll replace the information I know. I know the pH is 8.5. And I'm going to try to solve for the hydronium ion concentration. Now, in order to solve this, what I'm going to do is rewrite this in exponential form after I isolate the logarithmic function. So I'm going to divide both sides by negative 1 to get the logarithmic function by itself. And then I'm going to rewrite this in exponential form, and I get 10 to exponent negative 8.5 equals the concentration of the hydronium ion. And again, if I type this into my calculator, I get a really messy decimal. So I'm going to leave my answer at this. So therefore, the concentration of the hydronium ion in seawater is about 10 to exponent negative 8.5 moles per liter. Okay. For the third question, it says how much stronger is an acid with a pH of 1.9 versus an acid with a pH of 3.8. Now, there's a couple of different ways to answer this question, and we're going to look at one way. One way is to actually compare the concentration of the hydronium ion, so you can see how much stronger the acid with a pH of 1.9 is versus the acid with a pH of 3.8. So that's the method I'm going to use first. So I know I have a pH, I have an acid with a pH of 1.9, and I know I have an acid with a pH of 3.8. So I'll figure out the hydronium ion concentration just like I did previously. So pH equals negative log of the concentration of the hydronium ion. And so 1.9 equals negative log of the concentration of the hydronium ion. And I'm going to continue to solve for the concentration. And so for the acid with a pH of 1.9, there's a hydronium ion concentration. And same thing here, if I go through all the work, I get 3.8 equals negative log of the concentration of hydronium ion. And if I continue to solve this, I get 10 to the exponent negative 3.8 equals the concentration of H+. Okay, so it's the same method as what I did here. I would use the same method to solve it there. So now to figure out what the difference in the concentration, or in terms of the strength of the acid, I'm going to divide the two concentrations of the hydronium ion, and then based on that you can figure out how much stronger the acidity level actually is. So if I do 10 to the exponent negative 1.9 divided by 10 to the exponent negative 3.8, and I do this on the calculator, I get about 79.5. Okay, so what that means is that the stronger acid is 79.5 times as intense as the less strong acid. Okay, so therefore the stronger acid is 79.5 times as intense. Okay, so that's how much stronger it actually is. Now there is another way of solving the same problem as well, and what that does is it actually looks at the difference in the pH levels, and then based on the difference in the pH level you can figure out how much more intense the concentration of the hydronium ion actually is. So this is the second method here, find the difference in pH and then calculate the resulting hydronium ion concentration. And so the difference in pH, if I actually do this, is pH equals, we have one pH of 3.8 and one pH of 1.9. So you're going to look at the stronger pH, which is 1.9, and subtract the less strong acid from it, and you get a pH of negative 1.9. And now if I actually plug this into the formula to calculate the concentration of the hydronium ion, I get pH equals negative log of the concentration of the hydronium ion. And so negative 1.9 equals negative log of the concentration of H+. Divide both sides by negative 1, and I get 1.9 equals negative log of the concentration of H+. And oops, that's positive, since I divided both sides by negative 1. And so then I get 10 to the exponent 1.9 equals the concentration of the hydronium ion, which is actually 79.5. Okay, so this is just another way of doing it. So one way is to calculate the concentration of hydronium ion for each acid, and then based on that compare their hydronium ion concentrations, and you get about 79.5. Or the other method is to figure out the difference in the pH and use that difference to figure out how much stronger the hydronium ion concentration is, or how much greater the hydronium ion concentration is. Okay, one thing to note is that a pH difference of 1 corresponds to a 10-fold increase in hydronium ion concentration, whereas a pH difference of 2 corresponds to a 100-fold increase in hydronium ion concentration. So for every 1 unit increase, you're looking at a multiple of 10 increase in concentration of hydronium ion. So here you can notice that the difference in pH is about 2, so you can see that it's between 1 and 2, and so you can see that the concentration of hydronium ion is between 10 and 100 times stronger. Okay, the Richter scale is the second logarithmic scale that we're going to be looking at. So the magnitude M of an earthquake is measured using the Richter scale, which is defined as M equals log of I over I naught, where I is the intensity of the earthquake being measured and I naught is the intensity of a standard low-level earthquake. Okay, So you can see what the Richter scale sort of looks at on the right hand side here. And so depending on how strong the magnitude of the earthquake would be, you can see that the intensity would be different as well. Okay, so the higher the magnitude, the much more effective it is in terms of the intensity, the stronger the intensity. Okay, so for the examples here, the first example says, if an earthquake has an intensity that is 107.8, what is its magnitude on the Richter scale? So here we're given the intensity and we want to know what the magnitude is. And so I've started the question on a separate sheet of paper. And so I'm looking for the magnitude. I'm given the intensity. And so I'll plug that into the formula for the magnitude. And there's my formula there. I'm given the intensity, and so I'm just trying to calculate the magnitude. And so I get a magnitude of about 2.03. Okay, so an earthquake with intensity 107.8 has a magnitude of 2.03 on the Richter scale. So if I look at what that means on the Richter scale, that means it's the smallest quake people can normally feel. So that's roughly what a magnitude 2 on the Richter scale would look like. Okay. Okay, second question, or part B of the second question says, how many times more intense was an earthquake that measured 7.5 on the Richter scale than an earthquake that measured 6.2 on the Richter scale? So again, you're looking at comparing intensities. And so there's a couple of different ways of doing this question. Okay, one way is to look at the intensities of a magnitude 7.5 on the Richter scale and look at the intensity of the magnitude of 6.5 on the Richter scale. And then so what you would do is calculate the intensities for each of them and then divide the intensities. That's very similar to the pH scale question that we did earlier. Or the second way to do this question is to calculate the difference in magnitude and then solve for the difference in the intensity. Okay, so I'm actually going to use the second method because it's a little bit easier. And so I'm going to look at the difference in magnitude. And so that'll be the higher magnitude minus the lower magnitude. So 7.5 minus 6.5. And that gives me, I think those numbers are right. Oops, that should say 6.2. So that should say 6.2, and that should say 6.2. There we go. All corrected. And so you get a difference in magnitude of about 1.3. So this is going to be the difference in magnitude that I'm going to look at. So now if I just calculate the intensity, then it'll give me the comparison of the intensities of the two magnitudes on the on the Richter scale. So I'm going to plug that into the formula. And I get 1.3 equals log of the intensity. And I need to write this in exponential form in order to solve it. So 10 to the exponent 1.3 looks at the intensity. And I get about 19.95 as my comparison in terms of the intensities. Okay, so that means that an earthquake of magnitude 7.5 is 19.95 times as intense as an earthquake of magnitude 6.2. Okay, so again, one thing you want to recognize is that if you're looking at a difference in one magnitude, what that actually looks at is a 10-fold increase in intensity. Okay, so a magnitude difference of 1 corresponds to a 10-fold increase in intensity. A magnitude difference of 2 corresponds to a 100-fold increase in intensity. 3 would be a 1,000-fold increase in intensity, etc., etc.